Okay, good morning, everybody. Let's get started. Okay, any questions on the homework? Questions? Straightforward? Okay. If you have any questions, let me know. If I don't hear from you, then I'm going to assume there is no questions. Okay, so the last thing we're going to be covering with the sampling, we're going to be looking at practical considerations. And then we're going to look at quantization. We're going to look at aliasing. And we're going to look at down sampling and up sampling. Okay. So with that, we start with the practical consideration. And we said in the previous class, the first thing we have to consider when we are doing the sampling is that the signal that we're going to sample might not be band limited. What is it we have to do if the signal is not band limited? We have to take it through a low pass filter that will remove all the components above a certain frequency that we consider our bandwidth of the signal. So if the signal, or when the signal is not band limited, if the input signal is going to be not band limited to frequency FM hertz, and the solution is to use anti-aliasing filter. So this filter is an analog filter that is a low pass with a cutoff frequency that is omega cutoff is going to equal omega s over 2. So whatever our sampling frequency is, we're going to take it through an anti-aliasing filter that will remove all the components for a frequency that is greater than omega s over 2. Together? And this is what we have in the homework in the second problem, the use of the anti-aliasing filter. The second practical consideration. Go ahead. AA, anti-aliasing. Okay. The second is the mathematical model of our ideal sampler. What was the ideal sampler? The impulse trains, the deltas, the delta function. Okay. So the ideal sample, the delta function, pulse train, is not practical, is not physically realizable. And therefore, the solution is we can accomplish sampling via rectangular pulse train. And we call this sample and hold. What does that mean? So remember, when we looked at the sampling, how did we model the sampling? We had the signal, and then we multiplied it. So we have the continuous time signal, and then we multiplied it here by an impulse train. And this gave me xs of t. Together, sampling, we multiply the signal, the continuous time signal, with an impulse train to give me the sample signal. Now what we're saying is this impulse train is not physically realizable. So instead of multiplying with an impulse train, what we can do is we can multiply this signal with a rectangular pulse train. So 0t, 2t, etc. What do I get if I multiply the signal? If I have a signal and I multiply it with this impulse, with this pulse train, at the output I'm going to get a pulses that are going to change their height depending on the value that gets multiplied by the signal. This is time 0t, 2t, etc. Is that clear, everybody? So what is the impact of doing this? So again, what we're saying is, ideally, we multiply with impulse train, we get a sample signal. We're going to get a signal here that look like impulses, something like this. This is time, 0t, 2t, etc. Now what we're saying is, practically, there's no impulse train signal, and therefore what I can do is I can multiply it with a rectangular pulse that is very narrow. Anybody want to guess what the impact of doing this on the signal?
It's gonna like approximate it in a different way. It's like gonna stretch. You're taking it and you're kind of stretching it.
Correct, but we can make this as narrow as we can.
Sure.
Isn't it? So this could be very narrow. But what is it going from here to here? How do we know the impact of what we're doing on our signal? And it is straightforward. If I look at this signal and this signal, how do I generate this signal from this signal? Any ideas?
Fourier transform?
Okay, so I'm going to tell you how we can generate it. So to generate this signal is equivalent to the following. An ideal impulse train, 0t, 2t, 3t, convolved with a rectangular pulse. Agree? If I convolve this with this, what do I get? I'm going to get this impulse train. Make sense? How does this help me understand what's going to happen to the signal? I can look at the impact. So this is, if I were to just use this is the ideal case. But now I'm convolving this with a rectangular pulse. What is the impact of that on the spectrum of the signal? is going to multiply by multiply is correct because I'm convolving here. The spectrum of this is going to have the spectrum of this rectangular pulse multiplied by the spectrum of the signal. Does that make sense? Everybody? So here, instead of just convolving with this, if I convolve with the rectangular pulse, in the frequency, if I look at what happens in the frequency, so this is all time, in the frequency, what is the spectrum of the rectangular pulse going to look like? Anybody remembers? A sync. Excellent. Is it going to look like a sync like this? Or is it going to look like a sync like this?
Hopefully the first one.
The second one. The narrower the pulse in the time domain,
Okay.
the wider it is in the frequency domain. Does that make sense, everybody? So the narrower I make this pulse, the wider is the sync. The wider the time domain, the narrower the frequency domain. So what is the impact of this sync then? What is the impact of this shift? Whatever the spectrum of the signal is going to be multiplied by the spectrum of this rectangular pulse. You see it?
Yeah.
So if the signal that I'm trying to sample, for instance, has a spectrum that looks like this, what is the impact of this sync? It's going to somehow degrade the signal here, isn't it? And without the rift, this used to be a flat line. Well, it does not exist. Now, because of the rift that I added here, now I have a sync here that multiplies the spectrum of my signal. Does that make sense, everybody? So now it's going to distort my signal. However, if this is flat, then the distortion is going to be minimal. Make sense? So the narrower I make this, the flatter this is going to be, and the less impact is going to have on the signal. Together? Everybody sees that? Any questions? Questions? Is this concept understood? Okay. So we'll have probably a problem that would look at the impact of having this rectangular pulse in the homework. This is W. Okay. Another consideration is that the ideal low-pass filter that we use at the reconstruction cannot be implemented. Anybody remembers what the problem was with the low-pass filter? What did the low-pass filter, when we did the reconstruction? It requires an infinite, because it requires an infinite number of samples.
And additions and multiplications, not
Yeah.
multiplications.
Yes. Yeah, and it is non-causal. It requires an infinite number of samples. And therefore, practically, the solution is to have a practical interpolation filter. Filters are used. So what we do is we're going to take the samples. We're trying to reconstruct the signal. We're going to take the samples y of n. We're going to put them through a zero order hold h0 of t, and then we're going to pass it through a low pass filter. To get yr, we'll just call this y1 of t. So what does that mean? Let's say I have y of n. These are the samples that I'm trying to convert to an analog signal. So we have y of n. And y of n looks something like this. So these are the values that you have in your file, and we're going to convert it now to a signal. So what we're going to do, we're going to pass it through a zero order hold. What that is going to do is going to take each one of these pulses and is going to hold it like this. Second signal is going to be held like this. Third signal will be held like this. Fourth signal held like this. Make sense? So what did we get out of, what is the output going to look like? This is the output of this filter, of this zero hold block. So this is y1 of t. And then what we can do is we can smooth it. So we can take this signal that we have here, and if you pass it through a low pass filter, what is that going to do? It's going to remove these sharp edges. So I'm going to get an output that's going to look something like this. And this is my reconstructed signal. Is that clear?
So why does the low pass filter smooth that out?
I mean, that's what a low pass filter does. What does a low pass filter do?
So
It
that's
takes
fine.
a very sharp signal and it smooths it. Why? Because it removes high frequency components of the signal. Make sense? If I apply a rectangular pulse to a low pass filter, what is the output of the low pass filter going to be? If I have this low pass filter, so this is a low pass filter. This is the frequency. If I apply a rectangular pulse to it, what is the output going to be? It's going to look something like this. Make sense? Now we'll see it like more clearly when we look at the filters. But for the time being, the low pass filter, in order for the signal to jump from zero to a value, it has to have high frequency components. If I remove these high frequency components, the signal is going to grow gradually to that value. Together? So therefore, if I have a signal like this, I want to smooth it, what do I have to do? I pass it through a low pass filter. It's going to take all these sharp edges. So it's going to basically, all it's going to do is going to smooth the signal. And then I reconstructed my signal. Does that make sense, everybody? Okay. What does this zero order hold look like? What is the impulse response of the zero order hold? Anybody want to guess? Or not guess, just zero order hold. I send an impulse and I get a fixed value, isn't it?
Yeah.
So the zero order hold is going to have an impulse response that is h0 of t that looks something like this. 0, this is 1, and this is 10. Together? When I apply an impulse here, what do I get? A rect. The value of the impulse. And this is what this is doing. When I apply an impulse, I'm getting a rect, and the magnitude is equal to the input that I applied.
Yeah.
Agree? Everybody? Can you see it? Is this causal or not causal?
Non-cost.
Causal?
Because there's something before that.
Yes, it is a causal. So if I take the impulses through the zero order hold, this is the equivalent output that I get after the low pass filter. Is that clear? What does, again, everybody heard of zero order hold? Basically, it takes whatever value you give it here to generate a signal that is a constant at that value. So you give me 5, I generate an output that is 5 for 1 second. You give me -3, I generate -3 for 1 second. 10, 10 for 1 second. And this is what the output of the zero order hold would look like. Whatever value you give me at the input, I'm going to hold it for you. That's why it's called zero order hold. It holds that value for t seconds.
That makes sense.
Okay. So this is one way of doing or of bypass or removing or using the generation without the low pass filter. Another way is to use a linear interpolator. And with the linear interpolator, if you give me pulses that you're trying, if you give me y of n, the linear interpreter is going to try to connect these values together. So what's going to do, it's going to connect like this, and therefore convert these impulses into a continuous time signal. Does that make sense? So therefore, this red signal is YR of t. So this will connect samples with straight lines. Okay. What is the impulse response of this linear interpolator? Anybody? So if we have this linear interpolator,
I guess you gotta look ahead.
excellent, yes, you gotta look ahead. So if I apply an impulse that looks like this at 0, what is the output going to be? Well, the next, there's no values. All other values are 0.
So it goes to
0,
0.
0 here. So the output is going to look something like this. Agree? If this is 0, 1, 0, it's going to try to connect them. 0, 1, 0, 0, 1, 0. Make sense? So the impulse response of the linear interpolator looks like this. So this is our h of n.
So it always kind of tries to decay the value a little bit. Like if you want to think of it kind of like that. Like it always wants to try to decay it towards 0 based on what the graph kind of shows.
Well, what the interpolator is going to do, if there's no other, for the value that it has, it's going to generate a 1. And it's going to try to connect it to the next value. So if this was a 0 here, it went back to 0. If this was a 10, it's going to go up to a 10. Make sense?
Yeah.
So the impulse response overall, the impulse response of the interpolator filter is going to look something like this. Make sense, everybody? And again, you can see it because if it connects the previous point to the current point to the next point, if the previous point is a 0, 1, 0, it's going to connect 0, 1, 0. And that's what the impulse response, the output when we apply an impulse.
Yeah.
Okay. Is this... okay, one more question. How does this look like in the frequency domain? So again, I mean in this course and probably in everything now you do, everything you see in the time domain, you have to also mirror to the frequency domain. And they should be always consistent. That gives you always more insight on what the behavior of the system is.
Since it's limited in the time domain, it would be unlimited.
It is unlimited, yes. Now let me ask you this question, and if you know it, then good. If you don't, okay. How do I get a rectangular from convolution? How do I get this triangle from convolution? What are the two functions that if I convolve them will give me this triangle? Two rectangles. Excellent. So I'm going to show you how this problem looks very complicated, but with a little bit of thinking, you can break it down, and you're going to realize you have all the components that you need in order to know what it's doing. So the first thing we're going to say, oh, this triangle is coming from a rect convolved with a rect. If I convolve two rects together, what am I going to get? I'm going to get a triangle. Anybody knows that? Everybody knows that now. Know now, forever. Okay, so how does that help me? What I want to do is, I want to see what this looks like in the frequency. I do not know the spectrum of this triangle, but I know the spectrum of the rect. What is the spectrum of the rect? A sink. The spectrum of this rect, a sink. Convolution, the time domain, what is going to be? Multiplication, the frequency domain. So what is the spectrum of this triangle?
Sink squared.
Sink squared. Exactly. Sink squared. So therefore, if I look at this rect, in the frequency domain, this looks like a sink squared. Together? Now remember, what is it? All of this, what is it supposed to replace?
An infinite pulse train?
This all supposed to replace the low pass filter. Remember the ideal low pass filter. So all what we're trying to do is to replicate the impact of a low pass filter on the signal. Does that make sense? What does this look like if it is a sink? Sink squared. A low pass filter, isn't it? the components of the signal here, there's repetitions here, but this is going to decay, so you remove them. So it looks like I generated a low-pass filter. Is that clear?
Yeah.
Now, because this sink squared versus the rect in the previous one, the sink squared is going to be smoother in this range. It's flatter. And therefore, it gave me this nice looking signal compared to the rectangular pulse. Is that clear? So this ideal case, what I wanted a low pass filter that looks like this. All what we're trying to replace this ideal low pass filter. We said we cannot have a low pass filter. Now we see that this sink squared is mimicking a low pass filter. The sink is smoother, the sink squared is smoother than a sink. If I use a sink only, it's going to look sharper than this. Does that make sense? The sink squared is flatter, and therefore it gives me this nice looking signal. Now the same thing, I can take this signal and smooth it even more with a low pass filter. Make it look smoother. Okay. Any questions? Is that clear?
But you can only use this on a signal you've got recorded.
Because it is, oh, excellent. Now if I look at this, is this causal or not causal? Non-causal. So yes, I need to know the next sample before I generate the current output. I look and say, okay, the next sample is going to be 10, then I have to take my curve this way. Previous sample this, go this way. Yes, this is a non-causal filter. And remember, non-causal means it's predicting. Okay.
So, sorry, but how do these relate to the FIR and the FIR and IIR? Do these relate to that at all? Or
Excellent questions. FIR and IR are going to be digital filters.
okay.
These are all trying to generate analog filters.
Okay.
Does that make sense? So how this relates is that after we're taking these samples, we're going to operate on these samples with a filter. With me? And then we're going to try to generate the signal again.
But we're still digital here, right?
This is digital. This is we're trying to convert it to an analog signal. This is an analog signal now. This N is for the black, and for the red, it is T. Is that clear? With me? So going back to what lecture was it? Where did we start talking about? Okay, I mean, we can. Thought we had this more spelled out. Okay, it looks like we did not. Okay. So what we're saying is, what we're going to be doing, we're going to be taking an analog signal that is continuous. We're going to convert it using an analog to digital filter. We're going to have a digital signal. So now, if you like, this is a computer here. We're going to design an IIR filter, FIR filter. Then we're going to take this signal and we're going to convert it back to an analog signal. Does that make sense? So this is how what we're trying to do. We're going to take analog signal. Now it is in a digital format. We can operate on it with a digital or analog filter. Then we're going to generate it again. Make sense? But for what we're illustrating, imagine this does not exist. We converted this signal to digital. Now I want to generate it again. So I have a digital signal, I want to generate back an analog signal from it. Understood? Okay. Good question. Okay. Okay, let's look next at the aliasing effect. So we know from sampling theorem, for a signal to be reconstructed, we have to have the sampling frequency must be greater than twice the maximum frequency of the signal. If this is not satisfied, then we will have aliasing. So what we're going to do, just to better understand the impact of aliasing, we're going to look at sinusoidal signals, since they're easier to plot and generate and look at the spectrum for. So we're going to assume we have a signal, x continuous, that is equal to a cosine 2 pi multiplied by 100t. What is the frequency of this signal? 100 hertz, or 2 pi multiplied by 100 radian per second. Now what I'm going to do, I'm going to take this signal, I'm going to sample it, and I'm going to pass it through a low-pass filter. So this is an ideal reconstruction filter. So, and I'm going to sample it every t second. This is x continuous. This is going to give me x sampled of t. Together? Now, why am I doing this? I mean, this does not make sense, doesn't it? Like, why sample it and then regenerate it? But we're doing it just to understand the impact of aliasing. Is that clear to everybody? So this is not a system. I didn't want somebody to look at these plots like, oh, why will you ever sample and then just see there's something missing? Yes, it's just for the purpose of understanding the aliasing. Okay. Together? So we're going to start with our continuous signal. We're going to look at the spectrum of our continuous signal. What does the spectrum of the sinusoidal signal look like? This sinusoidal signal look like? The spectrum.
Spectrum will be limited.
It is limited. And what does it look like? I'm going to tell you what it looks like, but I want you also to remember how it looks like forever. This is what the spectrum of the sinusoidal signal look like. X continuous of omega or j omega. Together? It's going to have a magnitude of a pi and a pi, and it's going to have two impulses, one at 2 pi multiplied by 100 and one at negative 2 pi multiplied by 100. Anybody remembers that? Any objection to this? Make sense? Okay. Now this assumes this signal goes from negative infinity to infinity. Doesn't it?
Yeah.
What if this signal does not go from negative infinity to infinity? But it only ran over a finite amount of time. What is the spectrum of it going to look like?
It's gonna like feather out, like around those points, you're gonna have a couple more,
Yes, and where is that coming from?
because you didn't sample enough.
Okay, what else?
The sudden stop and start at like the ends of the signal.
What else? Again, like you're going to see, I'm going to answer now, and you're going to see that we have the answer to it. If I have a signal that exists only over a finite amount of time, what is that equivalent to? It is equivalent to taking a sinusoidal signal that goes from negative infinity to infinity and multiplying it in time with a rectangular window. Agree? If I multiply this with this, what do I get? A sinusoid that only exists from this time to this time. Agree? In the frequency, what is this going to look like?
Involving with the same.
This is going to be a sync convolved with
Those two lines.
these impulses. So how is the spectrum going to look like if it was only existing for a finite amount of time? It's going to look like a sync here and a sync here. The wider I make this window, what's going to happen to this sync? Always the reverse. If it's wider in the time domain, what's going to happen? It's going to get narrower. Wider, narrower. Wider, narrower. Eventually, it's going to go back to being an impulse. You see it? Okay. Okay. So let's see what happens if I sample this signal and t is equal to 1 over 400 seconds. And therefore, the sampling frequency is equal to 400 hertz. Is this greater than the Nyquist frequency? If it is 400 hertz? It is, because the maximum frequency here is 100. I need a sampling frequency that's greater than 200. 400 satisfies it. So this is greater than 2 multiplied by f max. Okay, so what I'm going to see is how the spectrum look like. How is the spectrum of this signal going to look like? I'm going to have the two impulses at 2 pi multiplied by 100, negative 2 pi multiplied by 100, and the magnitude is going to be pi over t. What's going to happen when I sample the signal? This spectrum is going to start repeating every omega s. So where is this going to repeat? Anybody? Centered at 2 pi multiplied by 400, and then add 100 and subtract 100. So this is going to be pi over t, pi over t. Make sense? 2 pi multiplied by 400, and therefore this is 2 pi multiplied by 500, 2 pi multiplied by 300. Does that make sense, everybody? That's what we see. This spectrum, as is going to repeat, and this is how it's going to look like. This, like whatever this shape is going to repeat, is going to be centered at 2 pi multiplied by 400. So this point here is going to repeat here. So whatever that shape is going to repeat at that point. Okay, so what is it we're going to do next? We're going to pass this through our reconstruction filter, which is an ideal low-pass filter. So since I'm sampling this at 400 hertz, what is the cutoff frequency for my filter going to be? 2 pi multiplied by 200. Agree? The cutoff is usually omega s divided by 2. So therefore, what I'm going to have at 2 pi, I'm going to have a low pass filter that I'm going to pass this signal through. What do I get at the output of this low pass filter?
The original.
My original signal, yes. So by passing xs of t through low pass filter, we recover x continuous of t. Now we said the cutoff by default is 2 pi multiplied by 200, but it can be anything from 2 pi multiplied by 100 all the way to 2 pi by 300. Agree? This filter, we have flexibility of how we choose it. Could be all the way from here, all the way to here. Any of these filters will recover back my original signal. Is there an aliasing or anything? No. Perfect. Now we're going to see what happens if we sample this signal. If t is equal to 1 over 150 seconds. The sample frequency is 150 hertz. Is this greater than 2 maximum frequency of the signal? No. So it's not. So we're not satisfying Nyquist criteria. Let's see what happens. So I'm going to come here. The sample signal is going to look something like this. We have the 2 pi multiplied by 100, 2 pi multiplied by 100, and now I'm going to have a repetition of this. Where is it going to be centered at? 2 pi multiplied by 150. Together? So at 2 pi multiplied by 150, which is going to be somewhere here, this is 2 pi multiplied by 150. I have to take this shape and center it here. If I do that, where am I going to have the components?
15, but 2 pi 50.
2 pi 50, excellent. I'm going to get a component at 2 pi 50. And where is the other component?
2 pi 200.
At 2 pi multiplied by 250.
Oh, yeah.
100 minus the 150 and 100 plus 150. 2 pi multiplied by 150. And I'm going to have the same thing in the negative frequency. Together? So now, if I pass this through a filter, the reconstruction filter, what am I going to get at the output of the reconstruction filter?
Different frequency.
A different frequency. X recovered of t is going to equal cosine 2 pi multiplied by 50 multiplied by t, which is not equal to the original signal. Is that clear?
So if it's audio signal, it'll be lower frequency, so it'll be like.
If it's an audio signal, I mean the audio signal is a low frequency signal. But if you if you have an audio signal, then these components are going to come back and overlap with these components. I mean, this is what's happening, aliasing. These components, the high frequency, are coming back and overlapping the original signals. Together? Everybody?
Yeah.
So, with the audio signal, so let's say this is your audio signal. If you sample it and you repeat the sampling frequency, you're going to get a repetition like this. If you did not, then that repetition is going to start overlapping like this. Then you pass it through a low-pass filter. You have these alias components that are added to your signal. Okay. So how does this look like in the time domain? In the time domain, this looks something like this. And I'm going to tell you why this is important in a second. So I have a sinusoidal signal that looks like this. What is the frequency of this signal? You don't know, but I'm going to tell you. It is the signal which is the 100 hertz signal, sinusoidal signal. That is a 100 hertz signal. So this signal is 100 hertz. The cosine, or the cosine that we created. Now what's happening here? I'm sampling this signal, and my samples are taking like this. Originally, I should be taking 2 samples per cycle in order to meet more than 2 samples per cycle to meet the Nyquist criteria. Instead, I'm not satisfying that. So instead, I'm taking samples very far apart. So I'm taking a sample here. The second sample is here. Continuing this guy. The third sample is somewhere here. And the same thing on the other side. There's a sample here. Now what am I generating? I'm generating a signal that looks like this. What is this signal? This is a sinusoidal signal, but what is the frequency of it? We don't. It's 50 hertz. Does that make sense?
Yeah.
Everybody? Clear? Ask me. Let me squeeze it, see if it make it more clear. Now if we continue with this process, this is going to look like this. So I generated a sinusoidal signal, but the sinusoidal signal, the frequency of it is 50 hertz instead of 150 hertz. Together? Where could you see this problem? If you go to MATLAB and you try to generate a sinusoidal signal, and you don't know anything about sampling theorem, and you generate a signal, what do? You create time samples, isn't it? You create like an index, and then you multiply it by t. You generate time samples, and you say, okay, generate cosine 100 times t. Make sense? So you end up with a signal that looks like this. This is the valid signal. Even though this signal, I wrote when I gave it to MATLAB, I told them plot 150 times t. But because the samples I've taken are so far apart, it's going to generate a sinusoidal signal. And I'm going to look at it and say, oh, it generated a sinusoidal. I asked it to do sinusoidal, it generated sinusoidal. But what did it generate for me?
Wrong frequency.
The wrong frequency signal. Yes. Is that clear? Makes sense? So you might go to MATLAB, generate your time index, generate the cosine or a sine, plot it, and look at it and say, look, it's a cosine, it's a perfect cosine, but it could be a perfect cosine of the wrong signal, exactly like this. If I went to MATLAB, if I want to generate this black sinusoidal signal, what do I have to do? I have to make my sampling time very small. I have to take a sample here, sample here, sample here, sample here, sample here, 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 here. Together? The sample time is going to be very small. If I went to MATLAB and I made my sampling time this big, then MATLAB is going to generate the sinusoidal signal, but with the wrong frequency. Okay. Now, just to finish this topic, now one way we can one method or one technique, we can visualize what happens with aliasing. Alias frequency or aliasing frequencies.
Doesn't trick have a K? Is that not trick?
Yeah. It looked tricky. Is to use the Carpenter's rule. Ruler. What does the Carpenter's ruler look like? You know the rulers that folds and become, you know it?
Like a speed square, or
No,
like the one that goes like this, or?
no. The one that goes like this.
Okay. Yeah.
Anybody ever seen this?
Yeah.
I don't think so.
There's a little pin on each.
Yes, little pin on each. You can expand it. And collapse it. Expand it, collapse.
Like a tape measure?
Well, each one is, it has a measure on it. I have one, I can bring it if. Okay, so let's see how this works. So let's say I have a signal x continuous of t equal to cosine 2 pi multiplied by 75 plus cosine 2 pi multiplied by 425. So what is the maximum frequency of this signal? $425. Now let's say we sample this signal at 200 hertz, and therefore we have a cutoff that is 100 hertz. So I want to see what I'm trying to do. I want to see what happens if I sample this signal and then pass it to a low pass filter with this cutoff frequency. And the way we do this is we generate this Carpenter's ruler. And the ruler length is equal to Fs over 2. So ruler folds So if I have fs over 2, that I'm sampling this at every 200 hertz, what is this length going to equal to? 100. So the length of this ruler is going to be 100. What is it going to be at the other end? 200, then 300, then 400, and so on. What do we do next? We mark the frequencies that we have of the signal on the ruler. We have a frequency that is 75. Where is it going to be? Somewhere at the 3/4 of the first one. So I'm going to have a dot here that is a 75. And then I'm going to mark the other frequency. Where is the other frequency going to be? It's going to be somewhere here at 425. Together? What do we do next? We collapse this ruler together. If I collapse it, collapse, I'm going to get a ruler that has a length of 100, and I'm going to see two marks on it. One mark is blue at 75 at this point, and one mark is red, which is going to be at this point here. Agree? And therefore, what are the frequencies that are going to be in my reconstructed signal? 25 and 75s. And 75 hertz. Is that clear, everybody? Okay. What is the other way of doing the same thing?
Or find the Nyquist criteria.
I mean, the other way to do it is to plot this. But you see, if it's one signal, one sinusoid, it's easy to do. But now if I have two sinusoids, it becomes a mess in here.
Yeah.
And you lose track of it. So that is a trick to just easily tell what signals are at the output of the filter. Okay.
So that, in that example there, it would have been aliasing.
Yes, I mean, apparently,
You want the output of the filter to, like, instead of 25 to have 425.
100%, yes. This filter, I mean, exactly correct. What I want at the output of the filter to have 75 and 425. But in order to get these, I have to have a sampling frequency that is greater than 850. Makes sense? If I sampled at greater than 850, then this will stretch much, much longer. When I collapse, I'll get back my original signal. Make sense? If the sampling frequency is not satisfying Nyquist, then I'm going to get something like this. I'm going to get alias signals. These are not the original signal. I'm getting an alias signal. Okay. The next thing we're going to look at is undersampling or downsampling and oversampling. And so let's start with downsampling. Now, of course, this is very useful when it is a sinusoid because it's a dot. But you can also use it if it is not a sinusoid, as long as you know how to mark it. Does that make sense? So it could happen like if the signal, for instance, has a spectrum that looks like this, I can just put a line from here and stretch it all the way to whatever that cutoff allows. Okay. Down sampling. Why do we need to do down sampling?
You don't have enough space.
Excellent. What if I have a signal that is sampled, however, I'm out of space and I need to reduce the size of that signal? What happens if I have a signal that is sampled, but my system is designed for a lower sampling frequency? I have my filters, for instance, I have a system where it is expecting a lower frequency, a lower sampling frequency than the signal that is inputted to it. So what we need to do in that case is we need to reduce the sampling of the signal. And we do that by downsampling. So let's look at how much we can downsample a signal. So again, we're looking at the signal, we're sampling it, we're getting x of n, we're sampling this every t seconds. If you remember, if I sample it like this, I'm going to get a repetition. Let's say this is the spectrum of the signal. This is the spectrum of the sample signal, xs of w. This is w. This is 1 over t. This is the bandwidth of the signal, wb. And we can plot this against omega. And this is going to look same thing. I mean, this is the same graph. That's the scale is going to change. Omega is equal w multiplied by t. And therefore, I'm going to have w multiplied by t in here. Together, this is what we've seen. Sample signal. This is the discrete time Fourier transform. Agree? Everybody? So this is what we know. Now what happens if I came to this signal and instead of sampling it every t second, I sampled it every m multiplied by t second. And assuming m is greater than 1, what am I doing? I'm reducing the sampling rate, isn't it? And instead of taking every second, if m is 2, I'm taking a sample every 2 seconds. See it? Okay. How is the spectrum going to look like?
Every pointer?
We'll see. So the spectrum is going to look something like this. Instead of 1 over t, now it's going to be 1 over m multiplied by t, isn't it? It's going to divide by that sampling. And now it's going to repeat the same thing. This is omega s. This is omega. This is 2 pi. Now I can also, I can plot x of e to j omega. So this is x of w, this is x of e to j omega. And x of t to j omega is going to have, what is this value here? W sub b multiplied by m multiplied by t. Agree? So whatever, remember, omega is equal to w multiplied by t.
So it is flat.
It's going to have the same shape. However, if I'm undersampling, this is going to get bigger.
And the magnitude's going to get smaller too, right?
The magnitude is going to get scaled, yes. It's going to be 1 over m multiplied by t, and it's going to be wider. Together? this comes directly. If it is a T, it's 1 over T, and WB is going to be WB multiplied by T. If it is MT, 1 over MT, WB multiplied by MT. Now the question is, what is the limit on how much I can reduce the sampling of the signal before I have aliasing?
When WBMT equals pi.
I want these to be, the limit is when these are touching. Are they?
So when WBMT equals pi.
When WMT is less than, we want it to be less than 2 pi minus WMT. Okay. So we want W sub M multiplied by MT to be less than 2 pi minus W sub M sub B multiplied by MT.
So would this be lossless compression?
It is not compression, but rather it is undersampling. So what this is doing, if you have a signal, in the first case, I'm sampling it like this. In the second case, I'm sampling it like this. Make sense? So this case, I'm taking a sample every this second. In the other case, I'm taking a sample, I'm jumping several samples. Make sense, everybody?
But you're losing data.
Yes, I'm losing data. However, I mean, what the point is, if I sample at a higher rate that I have to, so the Nyquist tells me the rate. But if I sample this signal, but I'm taking more samples that I need to. Make sense? I can reduce that sampling as long as I'm still meeting the Nyquist. So I can reduce the sampling and take only these rich samples if they satisfy still the Nyquist criteria. Make sense? And that is going to tell me by how much I can reduce my sampling and still have no aliasing, and therefore meeting the Nyquist criteria. So 2W sub M multiplied by MT has to be less than 2 pi, and therefore M has to be less than pi divided by WB multiplied by T, and therefore M has to be less than pi divided by omega sub B. Is that clear? Makes sense? So I can reduce, as long as M is less than pi over omega B, I can reduce the sampling, downsample the signal, and still be able to recover the signal.
Yeah.
Yeah, I guess like, it's like the question is, if you oversample, you still reconstruct the signal, but the question is that data loss, is that perceptible?
So no, this is the answer. Of course, ideally speaking, if I meet the Nyquist criteria, I should be able to reconstruct the original signal. Make sense? If I have a signal, if I'm meeting the Nyquist, I should give you back the original. If you sample it more, does not buy you anything.
Okay.
What does it buy you when I sample more? This is what it buys you. If I sample at a higher rate, these replicas are going to become farther apart. Agree?
Yeah.
And that will enable me to use a cheaper filter to recover my data. You see what you get out of more sampling is these samples, these replicas are farther apart. When I design a filter, when I build the filter that I'm going to use to recover the data, the expense of the filter is determined by how sharp that filter is. This filter is very, very expensive. This filter is much, much cheaper. Together? So if you're sampling at Nyquist rate, you might have to use a very sharp filter like that. If you're sampling at a higher rate than Nyquist requires, your replicas are moving far apart, I can use a cheap filter to recover the data. Make sense?
Yeah.
And real quick, I'm sorry, I must have missed, what was the subscript B for? Like, what would the?
That's the bandwidth of the signal. So this signal has a bandwidth that is WB. Thank you, everybody.